We can start. So, any doubts on that identification? Please be free. Yeah, yeah. Okay, okay. Anything else? Anything else? Yeah, that's a good question. Yeah, yeah, that's, yes. Any other questions? I will answer everything. I want to remember that. Your all questions are valid questions, yes. See here, normally, suppose I assume a model theta 1 P1t plus theta 2 P2t plus theta n Pnt plus epsilon t. Now, what happens, you see, if the system is linear, because you know this P1, P2, they are yk minus 1, yk minus 2, uk minus 1, uk minus 2. That is understood. Linear systems. So, while doing the linear system identification, let me first answer his question first. Linear system identification, you sit in the computer, you start giving the ANA, you start with ANA, first you fit a linear model with first order model. First you give NA is equal to 1, NB is equal to 1. First you start here. I'll tell you the problem later on. It is not correct. Suppose you are not getting good response. Now when you give NA is equal to 1 and NB is equal to 1, your model, so your model is YK is equal to theta 1 YK minus 1 plus theta 2 UK minus 1. Now the question is, you start with NA is equal to 1 and NB is equal to 1. See the interesting thing which will come up now. And you estimate. So how many parameters we are estimating? 2. Okay. Then you find that things are not okay. The predicted outcome. Then what you do? You do NA is equal to, increase it. NA is equal to 2 and NB is equal to 2. If you do it, then your model will be, YK will be theta 1 YK minus 1, theta 2 YK minus 2, theta 3. How many parameters? Will total number of parameters. You see here, total number of parameters is equal to 2. Now if you make this one, the total number of parameters becomes 4. And you find things are not okay. You go on increasing, right? Go on increasing. Now let's do it. Now things are not, interesting things will come. Now suppose you make it NA is equal to 5, NB is equal to 5. So how many parameters total? 10 parameters. Then you can go on doing it. And you find that at what point it is doing perfect, then that is okay. In linear system identification, normally what we do, we gradually increase by trial and error. Okay. And we see which terms, which one model will be fit, perfect, right? It is because by increasing the NA, NB from 1 to 2 or 1 to 10, the total number of possible parameters increases from 2 to 20. Right? But the real problem comes, suppose the system is nonlinear. Suppose the system is nonlinear. Now you will find, I have got the slides, I don't know here, I think let me go to that slide, 1 minute, so then you can know it, 1 minute. 1 minute. Yesterday I was teaching that you just do trial and error. You sit in the computer, you first fit a first order model, not good, second order model, third order model, fourth order model, and at least fifth order, sixth order is fine, right? Now the real problem comes with the system is non-linear. Then non-linear, then there are many things. First thing, what is the maximum lag, NA and B? And what is the degree of nonlinearity? Second order quadratic nonlinear, cubic nonlinear, right? In a linear system, by changing it in the computer, the total number of possible parameters changes from 2 to 20. Now we saw it, right? But in nonlinear system, if you are doing the same thing, sitting in the computer, you see the number of possible parameters, 16, 31, 136, you see, 5,000. So you cannot do such type of trial and error sitting in the computer if it is non-linear. Linear systems, we do it like that, right? So in system identification, there are two things. What are two things? Now see here, yt is equal to theta 1 p1, theta 2 p2, theta 3 p3, theta n pn plus epsilon. This is the model structure, right? Two things important. One is you are fitting a model. You are getting the measurements yt, right? Also regressors. Now the question is, which term to be included into the model? Because I show you in the nonlinear system, under your assumption, the total number of terms is going to thousands. Then which term to include in the model? Because once you know which term to include in the model, then estimating the corresponding parameter becomes easier, right? So system identification has two issues. One is the structure selection problem. What is that problem? So I will give an example now shortly. Structure selection problem. That means out of all possible things, which terms has to be included? And then is parameter estimation. Then parameter estimation. And out of which structure selection problem is the most difficult problem, especially in the nonlinear system identification, because which term to be included? Because once you know which term to be included, other things become easier. I'm just giving an example. Suppose I give you a signal. Suppose I give you a signal f of t. Suppose I give you a signal f of t is equal to 10 sine omega t plus 2 sine 11 omega t. Suppose. And I ask you, just giving a prior information that this is a Fourier series. This is a Fourier series. This is for the prior information. Okay? Now you fit a model, Fourier model. I don't tell you which frequency component is present. I say that I gave you this data, you fit a model, and the model will be approached as Fourier series. So what you will do? You will use a model of this form. You will use a model of this form, theta 1 sine omega t plus theta 2 sine 2 omega t plus theta 3 sine 3 omega t, right? Because I have told you that it is a Fourier series, right? And out of which, if you fit the model, you will find theta 2, theta 3, theta 4, theta 5, they all will be almost 0. Because that signal doesn't contain that, right? So you will find only theta 1 and theta 11. So we can, which the mechanism we should use to do these things? Which terms are present? That is the extremely important part in system identification. Say for example, mass spring damper system. Mass spring damper system, everybody knows it. That the dynamics, what is the dynamic? The dynamics. Mx double dot plus fx dot plus kx is equal to u, right? Because someone has found it out, so therefore you are saying that. But how do you know it? Whether it is x double dot or x double dot q. Initially, suppose you are nowhere there, right? You have been given a data, you see, this is the data, this is the mass, and I am applying a force, I am measuring the displacement. Input and displacement data is given. Now you fit a model. What you will get? You don't know anything. So that means whether x double dot will be there, x dot will be there, or x will be there. These are terms. How do you know it? So which one is important? Term selection is the extremely important problem. That is called the structure selection problem. Okay. And second thing is, and I am not answering that thing here because we work in system identification in the structure selection problem because we know the parameter estimation problem is straightforward. Once you know the structure, it's simple algebra. Okay. Then another thing is, because yesterday I did not tell you, think in this way. I have got a vector like this. I have got a vector like this. This is the vector, let us assume this is the vector yt. Now you approximate it. You approximate it, right? This is what we are doing in identification. See, the first approximation I am doing it. I am taking one vector here, another vector here, I am approximating, right? This one plus this one is equal to this one, right? Another one. The same yt is here. The same thing I am approximating. If you sum them together, it will be like that, yes or no? Because I can sum all these vectors and I will come to this point, yes or no? So same thing can be approximated by so many different ways. How many possibilities are there? Infinite possibilities. Now which one you will prefer? Naturally you will prefer less number of terms. Which terms? That is the point. Which terms? Our experience says 700 data points is sufficient to identify any system. That is from our experience. Around 15 to 20 terms are sufficient for a reasonable good nonlinear system. 20 terms is sufficient. Don't go beyond that. If they are beyond that, then there is some problem. Right? Then which terms? Which terms you should select? So that is the structure selection problem. Now coming to your question, system identifiability. Suppose now here you see a relationship. System is yt is equal to theta 1 yt minus 1 plus theta 2 ut minus 1. This is the actual system, right? Now what I did, I use a feedback where feedback is equal to k into y. Now I substitute here, then this equation will change. The equation will change, right? So, and you identify that equation. So you identify the entire system, but the system actually, there is a term y, there is a term u, but by that feedback, this y is getting replaced by k into u. So the identification is lost. System has got a y term, but because you are doing some manipulation here, so things are changing. I'm giving the example, it is not clear yet, I'll tell you one thing here. You are all electrical engineers, right? Electrical engineers. Anybody has taught induction motors? Induction motors? If I got idea, then I can discuss. See what happens. Okay. If not that, let me explain with this way. Signal flow graph. Signal flow graph, you do it. Now suppose this is x1 and this is A and this is x2 and something here. What is x2? What is x2? A into x1. This does not mean x1 is equal to x2 by A. Got a point? x2 is equal to A into x1, right? This does not mean that x1 is equal to x2 by A, because this is the signal flow algebra is different. Because here this does not permit signal to transmit in the other direction. Okay? So equations, you see here, I'm just giving an example here. Suppose the system is yt is equal to theta 1, I'm just doing it here. Yt minus 1 plus theta 2 ut, this is the actual system, right? I use a feedback ut is equal to k into yt. Suppose I use a feedback, ut is equal to k into yt. Now, if I substitute here yt is equal to theta 1 yt minus 1 plus theta 2 into k into yt minus 1. Clear? Right? So that is equal to theta 1 plus k into theta 2 into yt minus 1. Do you understand these things? So this one and this one, they are algebraically equivalent, right? Because this is the same thing. Yt is this one, now ut is this one. Substitute that value and put it. But identifiability is lost. Because here, the system has got only y, u is not there. Whereas actually the system has got y, u. You got my point? This is called the system identifiability is lost. Yeah, there must be a term in terms of u, but it is no longer there. Okay. So, there are so many things has to be, the system identifiability is lost because of the closed loop system. System becomes closed loop, then identifiability is lost, right? But important point is the structure selection, not the parameter estimation. Because around 90% of the system identification literature is flooded with parameter estimation. That means the structure is known, but the real story is the structure selection. Because once you know the structure, the parameter estimation is straightforward algebra. So system identifiability is lost. Clear? Okay. So you are all academics, so you can say what we teach, the E is equal to minus n. When I was teaching electrical technology, while I was in REC, I was telling these things. Sometimes in machine theory, I taught 3 years I was teaching machine theory in Auckland. E is equal to minus n d phi by dt, electromagnetic induction. Now we say it, the negative sign is not the arithmetic negative. Negative sign is essentially reflects the Lenz's law, which tells that the effect always opposes the cause. Now this negative sign is not a arithmetic negative, I always say that. This is not an arithmetic negative, it maps, it models the phenomena of Lenz's law. See here. Lenz's law, what it says? E is equal to minus n d phi by dt. What it says? The voltage which will be generated and the corresponding current and the corresponding flux, it will oppose that, right? So it is the Lenz's law which is getting modeled or represented by a negative sign. Got a point? So those type of concept has to be there, right? Okay. Did you people did the assignment yesterday, the tutorial? Okay, you've done it. Okay. I'm coming to this point. This is which lecture? Lecture 6, 203, this is lecture 6. Yeah. Today with these 3 lectures, you will know about adaptive control. The basic thing is, am I sitting, is all right? Okay, then I'll start sometime later. Yesterday what you did, you have got a system. You generated the data applying a pseudo-random binary sequence. You collected the entire data and use it in the identification. Clear? These things you have done it, right? PRBS sequence is given. Then there is the ID data object in identification toolbox. Just put it ARX, ARMAX or anything will do. That type of estimation is called the batch estimation. That is called batch estimation, where you use all the data together, right? That we will not do in control engineering. Batch estimation, we have to do as the data comes, one after another, one after another, you will go on estimating it. You will go in. So that is called the online estimation, and it is coming under the category of recursive estimation. Recursive estimation, okay? Let us see the concept of recursion. You see, first let's go to the concept of recursive computation. That is only necessary now to understand. Now suppose I want to calculate the mean value of a sequence of samples. I have got 1000 samples data. I want to calculate the mean value. What is the mean value? I have got the samples. I have got samples Z1, Z2 up to Z1000. What is the mean value? Z bar is equal to sigma. Yes, sigma I is equal to 1 to n Zi divided by 1000. Sorry, divided by n. Right? I take the entire, all the samples, add them together, batch estimation, right? So how many storage space I require? 1000. 1000 storage, I have to store everything and then add them together. Clear? Batch estimation. Now let us do the same thing recursively. Recursively, right? So assume like that you are here, the data sample is coming, and you have to calculate the mean value, right? First sample comes. The first sample comes, what is the mean value? Mu1 cap. Mean value mu1 cap will be equal to Z1 because you have got only one sample. So the mean value is mu1 cap is Z1. Clear? The second sample comes. When the second sample comes, then mu2 cap should be equal to, first I am writing the general formula, Z1 plus Z2 by 2, that is equal to Z2 by 2 plus Z1 by 2. Clear? That is equal to Z2 by 2 plus half of what you have estimated before. Third one, the third sample comes. What is mu3 cap? Z1 plus Z2 plus Z3 by 3, right? So that is equal to Z1 plus Z2 by 3 plus Z3 by 3, right? Now that is equal to Z1 plus Z2 by 2 into 2 by 3 plus Z3 by 3. Is there any problem? I just manipulate it. That is equal to 2 by 3 Z1 plus Z2 by 2, that is equal to mu 2 cap. That is equal to mu 2 cap plus 1 by 3 into Z3. That is called mu 3 cap. Right? So, as the samples comes, what I am doing, so in general you will see the general mu n cap, in general the mu n cap will be n minus 1 by n into the previous estimate, mu cap n minus 1 plus the present sample 1 by n. This is the recursive computation. How many storage space I require? 2. 2 storage, right? Most of the batch processing algorithms, not all, I will tell you, not all, most of the batch processing algorithms can be made recursive. That point I am not explaining here. Most of the batch processing algorithms, where you take the entire data and do it, can be computed recursively by simple algebraic manipulation. Right? So similarly, now what we do it now in least square, batch least square, we will change it to recursive least square. Because that is what I need it. That is what I need for my adaptive control. Because each time instant, when data is coming, I will estimate the parameters and design the controller. We'll see. Okay? Now the same, I'm again repeating the point. All the batch processing algorithms can be made recursive or online estimation, real-time estimation or online estimation, the same thing. Here, suitable for online processing. Batch least square is computationally expensive for online estimation. In real-time systems, we require fast convergence, efficient memory use, update of estimates as new data arrives. Recursive least square or RLS fits these things. Suppose the system equation is yt is equal to phi transpose t theta plus epsilon. You see what I'm doing here? If yt, I'm just writing 3 terms, is equal to theta 1 yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1 plus epsilon t, that is equal to yt minus 1 yt minus 2 ut minus 1. The parameter vector is theta 1, theta 2, theta 3 plus epsilon t. Clear? I am taking only 3 terms without making complex. That is equal to, this one is called the observation vector. This terms is important. This is called the observation vector. This is called the observation vector. So this is equal to, as I told you, any vector means it must be column vector. If it is row vector, then you transpose it. That is the standard practice. So that is called to phi transpose t into theta plus epsilon t. Where phi transpose, phi t is the observation vector. Any problem? Again repeating, any vector in engineering is a column vector. If in your expression you find any row vector, you transpose it. So now that means here, by definition, phi t is equal to yt minus 1, yt minus 2, ut minus 1. This is the column vector. Vector means column, right? Now suppose your system is yt is equal to phi transpose t into theta. And I want to minimize this particular modeling error. We will talk about lambda later on. Just don't worry, why I want to minimize this error, right? Now, the batch processing says, batch processing will say theta cap is equal to say capital phi transpose, all the data is there, into phi inverse into phi transpose y. As I told, y is equal to x theta, x transpose x, whole inverse x transpose y. The same thing here, phi. Phi transpose phi inverse, phi batch processing. This is the theta cap batch. Theta cap batch is like that, right? There is a way to derive the equations, how to get the recursive formulation. That I am not going by, that itself will take more than 1 hour. That x, in this example, that x is phi. Here in this, xt is equal to phi t. That's same thing. Because while making the class notes, this theta cap recursively can be computed. Theta cap t plus 1 is equal to theta cap t plus kt plus 1 into epsilon t plus 1. So these are the 4 equations which we will use to recursively compute theta, right? Now I will discuss on this. I am writing this equation in different way. Let us write down these equations, same equations. I am writing theta cap t is equal to theta cap t minus 1 plus kt into epsilon t. Do you understand this thing, first equation? Theta cap t plus 1 is equal to theta cap t plus kt plus 1 plus epsilon t plus 1, right? So I am writing in different way. Theta cap t, instead of t plus 1, I make it t. So once you make it t, then the t will become t minus 1. T minus 1 plus kt into epsilon t, right? The standard recursive computation in any signal processing or control or any subject, the present value is equal to the past value plus some gain and error. Standard formula. The present value is equal to the immediate past value. So immediate past value plus some gain into error. This is the standard structure of most of the recursive algorithms. The present value is equal to the immediate past value, theta cap t is equal to theta cap t minus 1, plus some gain into error. This can be derived. We can derive it. Mathematically, we can derive it. It is not a big issue. It's not a very big issue. Derivations, I don't know whether I've given in here, but usually we ask the students to derive it. So now here, you want to estimate recursively, so present value of estimate is the previous value of estimate plus gain and epsilon t, the current error. Now here to estimate these things, you see here, you are estimating theta cap. So theta cap at a time instant t. Here you must be careful where you are. You are at time instant t. So if you are in t, what you know? If you are today, you know what we have discussed yesterday? So you know theta cap t minus 1. That is known. No doubt. So to compute this expression, this is known. This is known, right? Only because you are at time t, so you have to know what is this. And you have to know what is this. Because to compute theta cap t, right? Theta cap t is equal to theta cap t minus 1, which is known, plus some gain and error, right? Present error. So you have to compute kt and epsilon t, right? Now see, what is kt? Now see here, this expression, equation 3. kt is equal to pt minus 1 plus xt or phi t divided by 1 plus x transpose t pt minus 1 into xt. Do you understand these things first? kt is equal to pt minus 1 into xt, right? 1 plus x transpose t pt minus 1 xt. Clear? What is xt? xt, that is a phi t. That is the observation vector. So you are at time t, you are observing the signal. So xt you can formulate. Now you can formulate xt. We can formulate because xt. Clear? We can, because we are at time t. We are at time t, so we must formulate xt. That is there. That is xt is equal to yt minus tau, yt minus 2, yt minus 3, ut minus tau, depending on the model. So you know it. So you know you can formulate xt because you are at time t, you are getting the measurements, right? To compute kt, you require pt minus 1. P is the, I'm coming to that point, P is a covariance matrix. You see, this expression cannot be computed without knowing pt minus 1. See this expression. kt is equal to pt minus 1 xt divided by 1 plus x transpose t pt minus 1 xt. xt you can formulate. What is pt minus 1? What is pt minus 1? pt minus 1, you don't know it, right? Okay. Now the recursive computation, there is another catch words. I am just telling the catch points. You start doing something recursively, right? Any recursive computation requires one initialization, because where to start? Where to start? The present value is equal to the previous value plus some gain into error, right? Now what is the previous value? Previous value where? Previous value is 1,000 years before or 2,000 years before. Where the previous value? There is no previous point, right? So you have to assume some previous value to start with. So all recursive computation, all recursive algorithms requires some assumption that where to start. Got my point? Just like we said, whether chicken is first or egg is first. It's a difficult problem. You have to assume something, right? You understand these things? So that is an initialization phase. So you You assume all recursive computation. You have to assume because you see here, see where I am coming from. Let me just summarize before I proceed further. Theta cap t is equal to theta cap t minus 1 plus kt epsilon t. Theta cap, you are at time t, so theta cap t minus 1 is known. So to compute the entire expression, you must do kt and epsilon t. Epsilon t will come later on. Now kt is pt minus 1 into xt divided by that. You are at time t, xt is the observation vector, you can formulate it. Because you are getting the data, you formulate xt. So in this expression, xt is also can be known. But what about pt minus 1? Pt minus 1 is not known. So you have to assume. So not only that, in all the recursive algorithms, there must be some initialization phase. There must be some initialization phase where you assume what is theta cap 0, p 0. When you start it, what is the initial value? You have to assume it. Otherwise, you can start anywhere, right? You assume that, then you start. Now, you are assuming these things. Now, this pt minus 1 is known, right? Because you are at time t. So, kt is known, everything is known, you got kt. Now, this pt, that's my initialization. Pt is equal to I minus k. See what is pt? What is pt? Let us write down. Let us write down. pt is equal to I minus kt into x transpose t into pt minus 1. Right? So now kt is known. Kt is known. xt is known because you have formulated that. Right? Now you can know pt. Right? Now once you know it, then this is straightforward. You get the current value, you get the current value, epsilon t, the error, epsilon t is equal to yt because you are getting the value minus x transpose t into theta cap t minus 1. Epsilon t. In recursive computation, when there are set of equations has to be solved, you have to first identify which one has to be computed first. There are 4 equations. Which one has to be computed first? Now you see here, in this case, this one cannot be computed first because it requires kt plus 1 and kt plus 1 is the third equation, right? So first thing is, I'm just doing it here. First you do this one. First you compute this one. I will give you the annotated copy of this lecture note. Then after you do this one, then you do the second one, this. Okay? Then this third one, this is fourth. Right? Second and third you can interchange, is not a big issue. Second and third you can do anything, but usually it's the case. First you compute the Kalman gain, this kt is the Kalman gain, and then second, then third, then fourth. Okay, recursive computation. Initialization, you should initialize the parameters. What is the initial value of theta? And P is called the covariance matrix. I am not entering into that. That is this matrix, this doesn't matter. So this P should be little high value. If you do not know the parameters, you should take it as a high value. Okay? Just initialize it. You will see now, the program. Exponential forgetting, I'll come back. See, this is what equation I've written here. So this one, you should do it first. This one is the second. This one is the third. And this one is the fourth. Kalman again. Pt into phi t. Lambda is the forgetting factor. I'll talk to that one. Just assume that is 1. Phi transpose t, pt minus 1, phi t. I'll come back everything here. I'm just showing here. Now see, this program has been written. I'm just telling you this program is very carefully. Step number 1. Kalman gain numerator is equal to p into phi. Is it clear? Can you see the Kalman gain numerator is equal to p into phi? You see here. Numerator is equal to p into phi. Is it clear? Kalman gain denominator is equal to phi transpose into p into phi, lambda plus. Now Kalman gain numerator, you see the program. Kalman gain denominator is equal to lambda, that is forgetting factor, I will come to that point, plus phi transpose p into phi. This is lambda plus phi transpose p into phi. Clear? Yeah? No, I'm using the forgetting factor, forgetting lambda, this one. That should be 1. No need, because I did not discuss now, I discuss shortly. It is lambda. What is the meaning of lambda? It is usually 1. Or what is lambda? I am coming to that point, just a minute. But the program is written like this, lambda. So Kalman gain numerator, Kalman gain denominator. So Kalman gain is equal to numerator divided by denominator. Clear? First equation is done. Then the covariance matrix update. P is equal to 1 by lambda, P minus Kalman gain into phi transpose into P. You see here? See, 1 by lambda, P minus Kalman gain phi transpose in P. See this equation? This equation is 1 by lambda, P is equal to 1 by lambda into P minus Kalman gain into phi transpose into P, right? Now see here, the same thing here in the program. See, P is equal to 1 by lambda into P minus Kalman gain KT into phi transpose into P. Clear? So K is computed and P is computed, right? And the error y cap is equal to this one. So error is equal to yk minus phi transpose theta, right? And then theta is equal to Kalman gain into error. Clear? Recursive square I am writing here. First equation, second equation, third equation, fourth equation. Any problem? Because why I am telling it? Because this is necessary for many cases, recursive computations. See the equations here and exactly the same way the program has been written, right? Okay? Now what happens? There is a term called forgetting factor. When new data, because you are estimating the parameters as data comes, right? As data comes in, you are estimating, you are modifying the estimate. So normally what happens? You give either equal weight for all the data or you give more weight to the recent data. So that is the forgetting factor lambda. That is? No, that is not varying. That is constant. You see, 1980s, when this recursive least square algorithm came up and all these things, people have done many research, the effect of forgetting factor. You just select this 0.9 instead of 1, make it 0.98, 0.99, this will work fine. It is not very critical in the performance of the algorithm. So therefore, the only thing that forgetting factor, you just forget by certain amount. Don't give equal weight to everything. Right. Yeah. Yeah. No, that will automatically taken care of whenever, if you derive it, that will automatically take care, because earlier we used to do it sigma epsilon square. Now I am doing it j is equal to sigma lambda k minus I epsilon I square. That's the only thing which I am doing here. If you do these things and do the differentiation, you will get that automatically, that expression will come. So instead of 1, if there is lambda, it means that you are giving more weightage to the recent data. Actually, you are not giving actually. It is, I'm saying this is not very important, because lambda is equal to 1. Instead of 1, you take 0.99. This should work. It's not a big issue. It's not very great. The performance of the recursive algorithms will not be affected much by these things. The only important point is any recursive algorithm is there must be some initialization phase. That's the point. And another point which I'm going to tell, and this is extremely important here, then before I go to the next lecture after some time, this point you will do it today itself. I'm telling you, suppose yt is equal to theta 1 dat, I'm just writing it here, theta 1 dat yt minus 1 plus theta 2 dat yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1. See this very carefully. Yt is equal to theta 1 dat yt minus 1 plus theta 2 dat yt minus 1, right? Theta 2 yt minus 2, theta 3 ut minus 1, where suppose theta 1 dat is known. Theta 1 dat is known. It is known. Now, if a particular, you see, this is yt minus 1, this is yt minus 1, right? Now, I can make it as theta 1 dat plus theta 2 dat into yt minus 1, right? One term, right? But in the yt minus 1, theta 1 dat component is known. So, theta 2 dat is not known. So, if something is known, bring it to the left hand side. So, my equation will be, the estimation equation will be yt minus theta 1 dat yt minus 1 is equal to theta 2 dat yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1. If something is known, don't estimate it. Bring it to the left hand side and other things you do it. We'll see to these things today in the next lecture when I talk about the minimum variance controller. Then I will connect these things, minimum variance controller here, and make it adaptive. Okay, we'll see.